Hello again, and we are now in chapter 11 that has to do with NLP, Natural Language Processing, which is one of the most sought after fields in artificial intelligence nowadays. And let's start with a game that's called, we call it Find the Mystery Word. In particular, there is a game called Semantle. I hope I'm pronouncing it correctly. And this is a game where it's an online game where every day they pick a word and you are supposed to try to guess what the word is. It can be any word in the language, and it will give you back a grade between, let's say, 0 and 100. The closer you are, then you're closer to the word. And what does it mean closer? It's a matter of language, of semantics. The meaning of your word should be somehow closer to the meaning of the word that they chose, and this is how the your suggestion is being rated. So they tell you, for example, in my screen capture here, that the nearest word of today, for the word of today, which was number 890, the nearest word that anybody guessed so far was 82.35 out of 100. And some other, and they tell you how to play it. But we are going to just explain a little bit how this works first, and the way they measure the distance or the similarity between your guess and the word that the game picked is done through something called embeddings, word embeddings, which are really the foundation of all or a lot of the natural language processing nowadays. Embeddings are vectors of numbers or floating point numbers that actually represent different words in the language, and they're sometimes very long. And there are many different sets of embeddings that are fixed embeddings that were created by training neural networks on um, large amounts of language, a large amount of documents, where they can eventually learn how words relate to each other and how words are used, and therefore they can sort of give words that have the same meaning or use the same way a certain kind of similarity or relations between them. So what we see here is a 2D projection of a particular set of embeddings, and this 2D projection is done using a technique called TSNE. So this is a TSNE or TSNE chart of certain words where the embeddings, which are vectors, multidimensional vectors, were squashed into 2D, and you can see all kind of interesting relations and grouping of the words. So you can see, for example, that fruit are in one particular area, and there are certain fruit that are very close to each other. Maybe the tropical fruit are more closer together. And here you have animals, and you see that crocodile and alligator are very close together. And here you have relations, or you have words that have to do with people. And you can even see relations like father and son. The relation between them, or direction, the distance and direction between them is very similar to mother and daughter. Or the same way you can say daughter and son, the distance between them is a lot like mother and father. So basically we know now that these vectors represent words, and they capture the meaning, the semantics of the words. So therefore we can take two words, translate them into these vectors, and calculate the distance between them. And this is exactly what the game does. It picks a word, you guess another word, and it calculates the distance and tells you this is how close you are to the word that we were guessing, to the word that you're supposed to guess. So we want to see if we can come up with a player that is based on a genetic algorithm that can guess the word. So the communication, so we have a game, we have a program that will emulate the game. It will pick a word, or we will tell it what word to pick to make it simpler, but it can also pick a random word. And then we will have a player trying to guess the word. So the player will send the word to the game, and the game will send back the similarity measure between 0 and 100. Also, the game is using certain model of embedding. We know what it is, but it feels that it will be sort of unfair to have a player that uses exactly the same word embeddings because maybe you can calculate the distance. You can use maybe this number to calculate the distance inside that and try to guess what the words, or try to actually calculate the words that are in this distance. So just to make it more separate, we are using a different model for the embeddings of the player and a different model of the game. As long as both embedding sets have a similar vocabulary and relations between words are sort of similar within each model, it should work, because all we communicate between is the actual word and not its representation. So the word cat may be represented one way here and a different way here, but still, if we have another word like dog, they will be close to each other, both here and here. So we will have the genetic algorithm try to basically come up with a vector of the numbers that represent a word, and then try to maximize the reward that comes back, or the similarity measure that comes back. Try to find a word that maximizes that. And because not every vector is actually mapping directly to a particular word, because there are more vectors, possible real number vector than words, if it comes up with a vector that doesn't exactly exist as a word, we will take the closest word to S and use that for the guess. So we are going to try to guess the word dog. Let's say that we make the game choose the word dog, and we will have the genetic algorithm try to find that word. So we are going to run that, and what we're going to see is at first it loads the model from a local file. The first time you will run that, it will load those models, the embedding models from the internet, and it will take a little longer to run it the first time. But then it will save it locally, and the first time that you run it will load it from a local file. And what happens now, in every generation, it shows you what is the word that represents the best guess. So you can sort of see the evolution of the guesses. So it starts with stories, which happen to be the closest word from all the words. We're trying to guess the word dog, to remind you. So it went from stories, and then bucket, and then toys, and then family, and then pet, and then it goes, after a while, it finally finds dog. So after 20 generations, it actually was able to guess the word, and then the score is 100. So also we use here a modification of the regular algorithm that we use. We know that if we reached 100, there is no point to continue the game. So we have a check into the algorithm that says if you reach 100, we know the rules of the game is that you cannot get more than 100. So you stop if you reach 100, and if not, you can keep going up to a large number of generations that is defined. So you're welcome to try this with other words, or to try to make some other variations of how it works. But meanwhile, here we will move to the second example. The second thing that we're trying to do here, another NLP problem that is unrelated to embeddings, it has to do with classification of documents. So there is a data set that is very common, and scikit-learn has it built in, and it's called the 20 news groups. You can see the news groups here. These are basically messages that were posted to news groups over time. So each document is actually a piece of text, a message that somebody wrote, and there are 20 different subjects here. And what we want to do is to take messages from two groups that are very close to each other, the motorcycles and the autos, and learn those documents, and then try to figure out, take a group of these documents that we haven't seen before and try to classify them. Are they part of the autos or the motorcycles? And the way we're going to do it here is use what we call n-grams. So n-grams is another technique. It is a little older than that has been there before embeddings ever came up, but n-grams are basically pieces of words. So it could be a unigram, or 1 gram is basically one word, if you look at words. And then 2 grams can be all the combinations of 2 words in a sentence. So here it will be these 2 words and these 2 words, and etc. And then a trigram will have all the combinations of three words. And we can do the same thing with characters. We can say, let's let's choose all the combinations of 3 characters, all the sequences of 3 characters that appear here and appear there. And basically we're trying to find out what combinations are more common in those groups and try to represent them as features. So all the 1 grams will be features and all the 2 grams will be features and all the 3 grams, and then we can say, okay, this group has these values, or every message will have certain values for those n-grams, and these will be the features representing that document. And if we can represent every document with the different numbers or combination of letters that it contains, and based on that we can try to classify and say, okay, this is more about motorcycles, or this is about cars. And actually this can work, but we want to see if we can minimize, or we can squash and use a very small subgroup or subset of those combinations, both because it will save us time and it will be a more compact way to represent the group, but also to understand what are the differences, so what are how we can distinguish between those two things beyond just using a black box model. If we can see what the model is actually using to distinguish between them, we understand a lot better how it works. So if we take the second program here, we can also look at the newsgroup classifier. So the newsgroup classifier is what will distinguish between the two groups based on the different combinations of n-grams, and you can see that we're using something called the TF-IDF vectorizer, which is a construct or a class in scikit-learn that can extract all those combinations. And we can say something like, let's have a word vectorizer, and let's take all the combinations of 1, 2, and 3 words as the n-grams, the word n-grams. And then you can say, let's say also one that looks at characters, and we can take all the characters that are between 2 characters and 5 characters, all those combinations, which will give us a lot of different features. And then you take all those features together, you unionize them, and you try to use that to train a classifier to distinguish between the two groups, and then you test it on a test group. But what we want to do is, as we will see, there are many of those features, about 50,000, and we want here to use a genetic algorithm to find a particular subset. So we have a genetic algorithm here at the Seoul newsgroups where we say, let's just find a subset of 100 out of the 50,000 or whatever combinations of n-grams that are possible to be used. Let's find the 100 that are the most important. That let's see if we can use 100, find those 100, and still get a good classification of the documents. And later on we will try with only 10. So when we are going with 100, we will run that, and it will take a while. And when it is going to converge and finish, we will look at the results. But you can see here that the number of features when it starts, it tells us that there are 51,280 features altogether. And we are looking to find the 100 features or combinations of words and letters that out of the 50,000 that will give us the most bang for the buck, that will give us the best results. So we can see here that this is the accuracy of distinguishing between the two groups, and we're trying to maximize it using 100 features. And as time goes by, we're getting better and better. We're here at 79%, and we will let it run for a while and see. I think it will run for 200 generations perhaps, and we will see the results when it gets there. So this is over after 200 generations, and we can see that we got to an 85% success or accuracy. And these are the 100 n-grams that were chosen, and it shows you here if it was a character, and so it would be these 4 characters, these 2 characters, and sometimes you will see that there is a word there. For example, here it's a whole word, and the word is technician. So it's great that we could do so well with only 100 features, but maybe we want to go further and see if we can do what we can do with 10. Let's reduce the 100 to 10, and let's see how well we can do if with just a subset of 10 features, only 10 combinations of characters or words. So let's do that by changing the subset size to 10, like it shows here, and run it again. This will run a little faster because we have a smaller subset that we choose, but it's still going to take a while, so we're going to wait for it. So the run is finished. So now we have a little bit less success rate. It's 76%, but it's still pretty impressive that we were able to get this kind of accuracy with only 10 features. And if we look at them, we can see that these are all basically pieces of words, character vectors, but they all seem to be pieces of words that maybe are, we can sort of recognize what the words are. So maybe we can try to go back and just capture whole words and remove the characters altogether out of the equation. So we can do this by going back to the newsgroup classifier here. And here, as we showed before, there is a character vectorizer and a word vectorizer, and the vectorizer that we're using is a union of both. What we can do here is mask that and only use the word vectorizer as the vectorizer. And if we do that and go back and run the program again with the 10 subset size, let's see what are the 10 words that we are going to find at the end. Notice that now it runs way faster because it only has, you see that it only has 2600 features to begin with, and it's looking for 10 out of those. So what we see here, we got 75%, which is very close to the previous one, and this time we can recognize all these words, and these are basically the 10 words that we use to distinguish between the motorcycle group and the car group, and that makes what we see here makes a lot of sense. So not only we have a very small subset that we can use, but it gives us some sort of an insight into how we can classify and distinguish between those groups. And that is it for this chapter. We will see you again at chapter 12.